Hey everybody! The purpose of this video is to go over some old ideas and maybe even see some new ones. Behind me on the chalkboard here, I've got a pair of coordinate axes and a couple lines plotted on that set of axes. What I want to look at is, number one, three things. Number one, I want to look at what those lines are and what they represent. Number two, I want to analyze the behavior of those lines as we move around this graph. And number three, I want to find out exactly what it means when these lines hit each other at this very special little area right here, where they crisscross each other. So I figure we start with a little bit of a review exercise. Given these lines, can we figure out what their equations are? Okay, so given the two lines that we have here. And I figure the way we'll do this is I'll knock out the purple one with you, and then I'll set you loose on the green ones to give it a shot. Okay, so let's start with the purple one. So given the purple line, the first thing I'm going to look at is the actual axes to see what the scale is. So I happen to notice that we've got a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now notice that I jumped right into saying that that was 1. And that's only because my eyes had looked over and saw that this was 5. So if this is 5 and there are 5 tick marks back to 0, that means each tick mark has to be 1. That would change, right? If, for example, this were 10, each of the tick marks would be 2. 2, 4, 6, 8, 10. If this were 100, they'd each be 20. If this were 1, they'd each be 1/5. 0.2, 0.4, 0.6, 0.8, and so forth. So you want to make sure you look at that. Also, look at the vertical to make sure it matches. Now, I drew this one very carefully so that 1 unit on X is equal to 1 unit on Y. You want to make sure, this is a little bit of an aside, when you're looking at graphs in your world or in your life, make sure that the axes are well defined. You can assume that two things are equal, but the numbers might say otherwise. More on that in later math classes. Anyway, so I noticed that this is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, copacetic. So if I count up 1, 2, I notice that this particular equation right here crosses. You probably can't see that, can you? It's probably pretty dark. Let me see if I have a lighter purple I could use. I'll use orange. That'll jump out better. It crosses right there at 2, at a Y value of 2. Now, more correctly, if you will, that point right there has coordinates 0, 2. Now, remember why. Or remember how come. At the y-axis, any place on the y-axis crosses through an x-coordinate of 0. So whatever the y-coordinate is, the x-coordinate is therefore 0. So that point right there has coordinates 0, 2. We're going to come back to that. We're going to make a table here in a little bit. Now, what you need to know to define a line is a second point, or a slope, whatever you choose to find. In this case, either one would be good, but I'm going to go with slope, just because I'm happening to look at it and seeing kind of how it's behaving. So to find the slope, we need to travel along the line to a certain reference point and then see what happened with the x's and y's as we made that move. So I'm going to go ahead and I'm going to bop over, let's bop over 2 points from 0. So if I travel along this line from my y-intercept of 0, 2 up to this point. Now this point here is 0, 2. The point we traversed up to here is over at 2, and it went up to a y-coordinate of 3. So to go from the y-intercept up to the next point, I went from 0, 2 to 2, 3. Now, what does that mean slope-wise? What does that mean slope-wise? Well, slope-wise, that means I traveled horizontally 2 units. You can see that in the coordinates. It went from 0 to 2, so it moved 2. And vertically, I went up 1 unit because I started at 2 and went to 3. So I traveled 1 unit vertically, 2 units horizontally. That tells me I have a slope of 1 over 2 or 1/2. Okay, remember that from before. Slope is rise over run. So it rose 1 unit and ran 2 units. That's a 1/2. Given those 2 pieces of information, we now know the equation of this line. The equation of this line is y equals 1/2 x plus 2. The 2 is the y-intercept, and the 1/2 is the slope that we got from our analysis of this these 2 points along this line. We could have used other points if you wanted to. If you wanted to use other points, that's totally fine too. We could have, for example, come out to this point right here. If you wanted to have done that, that's totally fine. I'll show you how it doesn't change anything. If you had chosen to come out to this point right here, now that point appears to be, let's just analyze what that point looks like. That looks like it has an x-coordinate of 4 and a y-coordinate of 4. So I'm going to go ahead and put that point right there. Okay, 4, 4. Now if you analyze the behavior, you have a couple choices now. You can start at the y-intercept and go to that new point. And if you analyze that, it looks like it ran 4 and rose 2. So if it rose 2 and ran 4, that's 2/4, which is the same as 1/2. You could put 2/4 in there, it's totally fine. So it doesn't matter which points you use, so long as you measure them correctly and then do the rise and the run correctly. Any point, the line, what makes the line is this uniform constant slope. So it doesn't matter what 2 points you use, you're always going to have that constant slope. So what I want you to do now is, I want you to hit pause on this video, and I want you to try to do the exact same thing I just did, but do it with that green line instead of the purple one. So you go ahead and hit pause, and we're going to come back and we'll regroup and we'll see what you got. Okay, go for it. Okay, doke. So now we're back. The green line up here. Now we have a little bit of our work done for us in that we have the point 4, 4, which is on both the purple line and the green line, which means that point satisfies both of the lines. We're going to come back to what that means in a minute. That's part 2 of 3. I'm going to make this easier for us to see and erase the stuff we already did with the purple line, because that's not relevant anymore. But the 4, 4, we can leave that up there. Now, I'm betting, just because we're human beings and we like to be efficient, I'm betting that those of us that found the second point found this second point right here. You used 4, 4 because it was already there. And why not use this one? I mean, it's right there. It crosses through the y-axis. So for free, you know it has an x value of 0. And the y value looks like it goes 1, 2, 3. So this bad boy looks like it's 0, 3. Okay, so now you know the y-intercept. You know that the y-intercept is +3 on the other side. That's perfect. The slope, we have to figure the slope out now, but I think we can do that. Starting here, if we wander over and then wander up, that might be easier to see. What have we done? Well, we wandered up from 3 to 4. That's a rise of 1. We wandered over from 0 to 4. That's a run of 4. That sounds like a slope of 1/4. 1/4 x plus 3. We now have both equations, one of the purple line, one of the green line, and we've got ourselves the actual mathematical formulas that generate these lines. What's cool about this is, once you have the formulas, you can figure out any points on the line anywhere. That's going to be part 2 of this video, is looking at that. So what I'm going to do is I'm going to go back to the purple line. I'm going to go back to the purple line. I'm going to go ahead and pull these points off of this purple line. Okay. Now, I'm going to go back to the purple one, and I think I was using orange because purple wasn't showing up very well. All right, purple line. Y equals 1/2 x plus 2. What we're going to do now is we're going to make a t-table to accompany our graph. Looking at these lines tabularly in a table form is another good way of seeing what's kind of going on with the behavior of the line. So what I'm going to do is I'm going to draw a little vertical line right here, and while I'm at it, I'm going to go ahead and I'm going to erase some of this over here because we don't even need that right now. We can come back to it if we need it. And I'm going to draw this, and I'm going to call this the x column. And what I'm going to do on that x column is I'm going to throw in certain numbers that we are then going to try in these equations. But we're going to try them with the formula first and then see how they kind of flip-flop over here to the graphs of the lines. Now, this might seem a little bit weird, but I'm going to put 0 kind of down here. Matter of fact, you know what? I'm going to put 0 up here. And then I'm going to go 1, 2, 3, 4, and I think you'll get the point after 4. And then I'm going to go backwards. -1, -2. Even though I didn't mark these on the graph, we could easily see where -1 and -2 for x would have to be by extending backwards our x-axis. These axes, hopefully you understand, I didn't mark them with arrowheads, but they do go on as far as we want them to go, depending on the context. For this case, this is no context, it's just the math. So what I want to do is, I want to actually take these x values and plug them into that equation and see what comes out. So let's just do that math first. Let's do that mathematics first. Okay, I'm going to start with 0 because I already know the answer. If I go 0 into this, I get 1/2 times 0 plus 2, which is just going to give me 2. But I didn't even have to do any math because I knew that the y-intercept of that equation was already going to be equal to 2 because that was the first point we found over here. What happens with 1? This is where it gets more fun. Well, that's going to be 1/2 times 1 plus 2. Well, that's 2 plus 1/2, which is 2.5. We can call that 2.5. How about 2? Well, that's 1/2 times 2 plus 2. That's 2 plus 1, which is 3. Now, hopefully you're seeing a pattern here. As the x values go up by 1, the y values are going up by 1/2. This should not be a surprise to you. The reason is because the slope is 1/2. That's what that 1/2 means. Every time the x goes up by 1, the y goes up by 1/2. Or every time the x goes up by 2, the y goes up by 1. You can see that right here. X goes up by 2, y goes up by 1. X goes up by 2, y goes up by 1. So if it goes up by 4, it's going to go up by 2. So going from 2, this is going to become 4. And this one would have been 3.5. So 2, 2.5, 3, 3.5, 4. Hopefully that's not a surprise to anybody. Let's see what happens with the negatives. Now let's first test it by running it through the equation and then see if it follows logically from the behavior of the slope. Going back to -1, that would be 1/2 times -1 plus 2. That's 2 minus 1/2, which would be 1.5. Well, 1.5 precisely is what it should be if we went backwards. It went from 2 to 1.5. Going forwards, 1.52, 2.53, 3.54, and so forth. So this one up here would have to be 1. Now what's cool about these numbers is you can actually see them on the graph. If you were to go to, for example, an x-coordinate of 1 and wander up, that one should have a y-coordinate, it looks like, of 2.5. And since I drew it to scale, it indeed does have that y-coordinate. If you went to 3 and went up to the line, that one should have a y-coordinate of 3.5. And indeed, since I drew it to scale, it does. It's right between 3 and 4. If you go to -1, it should have a y-coordinate of 1.5. Look at that. Looks like it is. And if we could get any point we wanted on this line by simply supplying the x values. Not a problem at all. Here's what I want you all to do now. I want you all to hit pause, and I want you to do the exact same thing on the green line that we just did on the purple line. Okay, in other words, use these same x values, but create another column over here for the green line, y equals 1/4 x plus 3. 1/4 x plus 3. I'm going to leave these next to us. I might clean them up a little bit while you're pausing. But what I want you to do is, I want you to come back and have this column still here, but another column that has the green line, which is the 1/4 x plus 3. Go ahead and pause, and we'll come back. Little ghetto, Sarah. We'll make it better for reals. Okay, green line. So we're going to go ahead and we're going to... Let's draw a little arrow orange here. There we go. Green line, y equals 1/4 x plus 3. Okay. So let's check and see what we come up with. If we start with 0, we know that this one's going to be 3, because it has the same behavior of the y-intercept that the purple line had, exactly the same one. Now, when we go to 1, what happens? Well, 3 is going to be increased by 1/4 of whatever the x value is. That x value is 1. 1/4 of 1 is 1/4, so you're going to end up with 3.25. Hopefully that makes sense. Hopefully that makes sense. Then, when you go to 2, you hopefully got 3.5. 3 was 3.75, and 4 was 4. 4 was 4. Going backwards, hopefully you see the behavior here. Every time x increases by 1, y increases by 1/4, which was the whole point. It was the whole point. It increases by 1/4 each time, which means going that way, it's going to decrease by 1/4. 2.75. And going this way, it's going to be 2.5. Okay, so working our way backwards, we're going to see these green points pulled from the same chart. So hopefully this is okay, having the two y values with the same set of x values. Hopefully that makes sense. Okay, now, what does that point mean for the behavior of these lines? Okay, so we already figured out that that point is on both lines, which meant when you were at that point's x value of 4, it generated the same y value of 4 on both lines. But what happens when it's not at 4? So for example, so far in this chart, we've seen numbers that are less than 4 up to 4. Let's take a look at some of the numbers that are less than 4. For example, 3. When we plugged in 3 to both equations, the purple line gave us 3.5, the green line gave us 3.75. There's a difference between those two numbers. 3.75 is a little bigger than 3.5. As a matter of fact, it's 1/4 bigger. 1/4 bigger. When it's 2, purple gave us 3, green gave us 3.5. That's a half bigger on the green line than the purple line. 1/4, half. When we plugged in 1, 2.5 to 3.25. That's 3/4 bigger. Green is 1/4 larger here, a half larger here, 2/4. 3/4 larger, 1 whole larger here. What you're seeing is when you wander this way, you're seeing the difference in the distances, vertical, between these two lines. That's 1/4 difference. That's 1/2 difference. That's 3/4 difference. That's 1 whole difference. You might see where this is going. If we go to 1, that would be 1 1/4 different. 1 1/4. And if you check your math, you'll see it's exactly what it is. 1.5 to 2.75 is 1 and then 1/4 more. The next would be 1 1/2. But what you're noticing is the y values here are larger than the y values here. So here's something that I'm noticing. When the x values are less than 4, the y values that are green are larger than the y values that are purple. I'll say that again. When x is less than 4, the y values that are green are larger than the y values that are purple. So let's make a little laundry list. When x is less than 4, the green y's are bigger than the purple y's. Let's make that a nice neutral greater than sign. That way it doesn't pick a side. When x is equal to 4, what's true about the y's? They're equal. That was the first thing we actually settled on. What I want you to think about now, I want you to pause, and I want you to figure out what happens when x is greater than 4. I want you to pause and figure out what happens when x is greater than 4, and then figure out how to justify it. We're going to extend our chart over here to help us. So give it a shot. Okie doke. Here we go. So x is greater than 4. Now, we can use the graph if you've gotten comfortable enough to recognize it from the graph. If you haven't, I'm going to start this chart all over again. If I had a big chalkboard, I would have more room for it. Hint, hint, department chair. So let's see what happens when x's get bigger than 4. Say 5, 6, 7, 8, 9, or 10. Now, we can use the equation for a couple of these to kind of get us started, and I think that's a pretty good place to start. When x is 5, for the purple line, that's going to be 1/2 times 5 plus 2. Well, 5 times 1/2 is 2.5, plus 2 is 4.5. Now, that should not be a surprise to anybody. That should not be a surprise to anybody, because we, on the purple line, went up by 1/2. Went up by 1/2 from the previous y value, which was 4. So now it's 4.5, and that, like I said, that shouldn't be a surprise to anybody. So that's right there. How about on the green line? Well, the green line is 1/4 times that 5 plus 3. Now, 1/4 of 5, it's a little goofy fraction, but 1/4 of 5 is 5 1/4. Excuse me. 1/4 of 5 is 1 1/4. 5/4, 1 1/4. So 1.25 plus 3 is 4.25. Now, notice what just happened. 4.25 is 1/4 less than 4.5. We're going to come back to that. It's 1/4 less. That little vertical distance is 1/4. Remember where else it was 1/4? Right here. Those of you that remember your geometry, which you can totally say, I don't remember geometry at all, these two triangles right here that are formed by these two lines, it's kind of like a TIE fighter from Star Wars. They're called similar triangles. Actually, they're congruent triangles. They're super similar in this case. But that's why these two distances are equal, because the external distance is the same. We'll come back to that. How about if we go to 6? Well, rather than filling up the chart with equations, we can just use the behavior of the line, knowing the y value is going to go up by 1/2 with each extra x value. So it's going to go 5, 5.5, 6, 6.5, 7, and so forth. The green line will do something similar, but go up by 1/4 each time. So this is going to go to 4.5, 4 3/4, 5, 5 1/4, 5.5, and so forth and so on. Now check it out. The difference here was 1/4. The difference here is a half. That probably wouldn't surprise anybody. Ooh, that not vertical. Since it's corresponding to this distance over here of a half. The distance here, 3/4. The distance here, 1. Up by 1/4, up by a half, up by 3/4, up by 1, up by 1 1/4, up by 1 1/2. The difference, of course, is that with the previous less than 4, the green line had larger y values than the corresponding y values on the purple line. What has happened here? What has happened here is the purple line has higher y values than the green line, which means that to complete this bad boy, when x is greater than 4, let's bring this down here into some open space, that means the y values on the green line versus the y values on the purple line are going to be less. Now the big takeaway is, could you have seen all of this by just looking at the graph? We just did a lot of work, a lot of good work, I think. But could you have seen all of this by simply looking at the graph? And the answer is a resounding, heck yeah! Because you can look at where the lines are above or below each other. For example, let me clean up the board. Let me get rid of all this wonderful work that we just did. It's all committed to the permanence of YouTube anyway. Leave the lines. Get rid of all the, I can leave the little verticals. I don't want to screw up the purple and the green. Could you have gotten all of that from just the green and purple lines? Heck yeah. All you've got to do is identify where they intersect. Where they intersect when x equals 4, the y green and the y purple. You know what we're going to do? We're going to do some symbols right now. This is ridiculous. Instead of changing color, let's just call this y little g and call this y little p for y green and y, the green line and the purple line. When x equals 4, y purple equals y green. How about that? That makes it a little bit easier. Okay. We discovered that when x was less than 4, we discovered that y green was greater than y purple, or that y purple was less than y green. Could you have told that without the charts? Absolutely. The purple line is below the green line. That means its y values, since it's below, are further down the y-axis. That makes perfect sense, I hope. And when we go past 4 with x, they crisscross. And then the purple line is greater than the green line. So mathematically, we refer to the x values and then analyze the behavior of the y values. Mostly a matter of convention. You could totally do it the other way too. It's just that we've been trained to look at these as the independent variables and these as depending on those independent variables. So hopefully this helped a little bit, kind of tying old stuff into new stuff. Hope it helped, and we'll see you in class. And Sarah, I'll talk to you soon about this.